find an expression for the deflection at point C. We're going to start by drawing a real moment diagram and a virtual moment diagram. So, for the real moment diagram, moment at point A and E is 0. And from A to B, so at point B, we're going to have linearly increasing moment of value force 120 times by the distance across which is acting 2, so 240 kilonewton meters. Same applies for point E. And then between point B and D, we're going to have constant value of moment of 40 kilonewton meters. Here is a neater version. Now, for the virtual moment diagram, we're going to apply a unit virtual force at point C, so equals to 1, since point C is where we're trying to find the virtual deflection. So basically, at whichever point it tells you to find the deflection, at that specific point you're going to apply a unit virtual force. And at point E and A, the moment is 0. So that's our virtual moment diagram here. Okay. We're actually going to split this structure into separate segments. So between A and B, we're going to start from 0 to 2, basically, because that's the length. So this interval of length we're going to call x between A and B, for which the real moment is going to have a value of 120 times by the length of the interval from 0 to 2, because it's linearly increasing, which we call x. So 120x. Now, for the virtual moment, we said we have a unit virtual force acting at midspan, and our interval is starting from 0 to 2. This is at 4. So x is this length we're looking at. So to find the virtual moment at this interval, we want to find the virtual force at this point and multiply it by our interval x. We know the virtual force at twice the distance, twice the length is 1. So at half of our interval is going to be 0.5. Using similarity of triangles, you can see triangle 1 and triangle 2. So 0.5 value of the virtual force times by x. So writing this here, 0.5 x, so half of x. Okay, next interval is going to be between 2 and 4. So this is going to be between point B and C. Now, the value for the real moment. This time is no longer linearly increasing, like from interval 0 to 2. Between 2 and 4, the one we're looking at now, you can see we have constant value of moment of 240. So we can just write this one as it is, 240. And now the virtual force between our interval 2 to 4, the length we said is x. We know the virtual force at this point, but we can't just do virtual force of 1 times by the length of x, because this is not the shape of our triangle. This is not where the virtual force stops acting at point 2 at the beginning of our interval. The virtual force stops acting at the beginning of our structure. So we're going to do the real virtual force of 1 times by the distance x, but we're going to have to subtract the length of 0.5x, which is also acting in our interval. So we said, what was it? 1.0x minus 0.5x, we're going to get 0.5x. Okay. Now, this structure is symmetrical, so I'm just going to leave it here. It's the same from C to D. And to find the virtual deflection, the formula would be integrating the real moment multiplied by the virtual moment over EI. And since we said we've only looked at half the structure and it's symmetrical, we're going to take into account the other half by simply multiplying by 2 in this case. Now, we split this into segments. So we're going to be integrating once from 0 to 2, the real moment, virtual moment over EI, and once from 2 to 4, the other segment we found, M0 MV over EI. And now, just substituting in what we have, from 0 to 2, the real moment we said is 120x in this case, multiplied by half of x, the virtual moment, over EI. When you multiply, so half of 120 is 60, and then x squared is what we get, plus from 2 to 4, the real moment is 240, multiplied by the virtual force, half of x, 0.5, same thing, over EI. And when you simplify this, you're going to get 120x. Okay. Now, simplifying further. This time we're going to integrate. So integrating 60x squared, you raise the power by 1, so 3, and divide the coefficient by the new power. So this is going to be 20. And then you substitute in each case 0 and 2. And then here, 120x, so increase the power by 1, and divide 120 by the new power, which is 2. And we're going to get 4 and 2. You integrate between 2 and 4. Let's not forget to divide by EI. Okay, now this is going to be, when you substitute x as 0, you're just going to get 0 for the whole thing. And when you substitute 2, you're going to get 160 over EI. And here, when you substitute 4, you're going to get 960. And when you substitute 2, 240. And subtract these, divide by EI. And multiplying everything by 2. Simplifying further, two times 880 EI. So the final form is 160 over EI. This is the expression for the deflection at C.